Hello there, Mr. Sutton here, bringing you the BC Calculus 7-9 Extra Practice Number 2 solutions on integral and p-series tests. For this problem, we're trying to find the radius of convergence for this power series. So because this is not a geometric series, we are going to have to use the ratio test. So I've got the limit as n approaches infinity. We need the absolute value of the n plus 1th term over the nth term for this. So n plus 1th term, we've got n plus 1 factorial times n plus 2 factorial times x to the n plus 1. All of that over, let's see, this will be 2 parentheses n plus 1 or 2n plus 2 factorial. And now down below, a little bit easier, it's just copying the summand as you see it there. It's just the nth term. So same change flip, we've got n plus 1 factorial, n plus 2 factorial, x to the n plus 1, and 2n factorial, all of that in my numerator. In the denominator, we have the 2n plus 2 factorial, n plus 1 factorial, and x to the n. And now it's time for a whole bunch of reducing. So let's take a look at the 2n factorial and the 2n plus 2 factorial, because those can get reduced together. So the key here is recognizing that 2n plus 2 factorial is really 2n plus 2 times 2n plus 1 times 2n factorial. So if I cancel out the 2n factorial and the 2n factorial that's part of this, all that's left is the 2n plus 2 and the 2n plus 1 downstairs there. All right, so all of that came from just the 2n factorial and the 2n plus 2 factorial. Now let's take a look at some more of these things. N plus 1 factorial and n factorial, those can get reduced to an n plus 1 upstairs. And n plus 2 factorial divided by n plus 1 factorial, if we cancel those, well, that's going to leave us with just an n plus 2 factorial up here. And also these x's can get reduced using our exponent rules. So this is just going to be x to the first power upstairs. So now as I take the limit as n approaches infinity, all these pluses and all these plus 1s and plus 2s that go with these n's, they can all be ignored. So this is essentially n times x, or n squared x. And down here, this is going to be 4n squared if I ignore the plus 2 and the plus 1. The n squareds are going to cancel out now, so that just ends up being absolute value of x over 4. Now for this series to converge, which we need to talk about if we're talking about radius of convergence, the ratio here, the nth ratio which we just found, has to be less than 1. In order to get the radius of convergence, we just have to figure out what's on the other side of this inequality when x has a coefficient of 1. So right now x has a coefficient of 1/4. To get rid of that, we just multiply both sides by 4. So I can write absolute value of x is less than 1, or less than 4 rather. So then that means the radius of convergence is just going to be 4. So that's choice D. For this problem, we're given this generic power series, and we're told b is an integer, and we also got convergence divergence at various values of x for this series in this table here. Based off this, we want to find the interval of convergence for the power series. So this seems a little tricky at first. The key is to get one of the endpoints, and then the rest of this problem kind of comes together. So the key to getting one of the endpoints is looking at what they gave us in this table. So we diverge and converge at different places. The key, though, is looking at this one right here. At x equals -1, it says we're converging conditionally. Well, the only place you can converge conditionally is at the endpoints. You can't converge conditionally between the endpoints. Everything between the endpoints converges absolutely. Everything that's outside the endpoints diverges. It's only at the endpoints that it could go one way or another. So that means that -1 is going to be our left endpoint. And we know it's the left endpoint, not the right endpoint. Well, we know it's an endpoint at all because of the conditional convergence, but it's the left endpoint because if you look to the right here, we're converging to the right and diverging to the left. So now we have to figure out the other endpoint. Taking a look further down the table, we see that we converge absolutely at 2 and diverge at 3. So that means our right endpoint is going to be somewhere between 2 and 3, including 2 and 3. Now, it can't be between 2 and 3. We know this because they said that b is an integer. If b is an integer, b is the center here. This is supposed to be halfway between the endpoints. So if you're taking -1 and averaging it together with something between 2 and 3, you're not going to get an integer. So we have to choose between 2 and 3. Now let's say that x equals 2 is the other endpoint. Well, negative 1 plus 2 over 2 is also not going to give me an integer. The only thing that gives me an integer when I average it together with negative 1 is this 3 here out of all my choices. So that means 3 must be the right endpoint. And the fact that it diverges is okay because we know at endpoints we could converge or we could diverge. And we could converge absolutely or diverge. It's either one of those could be an endpoint. So because that's our other endpoint and we're diverging there, we're not going to include 3 in the interval of convergence. But since we are converging conditionally at least at negative 1, we will include negative 1. So then I'm going to have, let's see here, negative 1 to 3, bracket on negative 1, parentheses on 3. So that's answer choice D. On this problem, they're saying the integral test can be used to determine convergence or divergence for each of the following series except which one. So this is where you have to understand the conditions of the integral test, which is that our function must be positive, continuous, and decreasing on an interval. It doesn't necessarily have to be the n value you're starting with for the series, but it has to, at some point you need to reach that continuity, positivity, and also decreasingness. So taking a look at choice A, this is definitely positive, and just considering n values of 1 or greater, this is definitely positive. It's continuous, because the only discontinuity is if you plug 0 in for n, and it's also going to be decreasing because your denominator grows as n grows. So because this is continuous, positive, and decreasing for n greater than or equal to 1, we would say that yes, the integral test will actually be able to figure out whether this converges or diverges. So moving on to choice B then, this is going to be continuous as long as the function is not, let's see here, as long as n is not whatever would zero out this denominator. So if I set this denominator equal to 0, I would have to subtract 4, divide by 6. I'm not going to get even an integer, let alone a positive number. So we're definitely going to be continuous for all values of n that are greater than or equal to 1. We're also going to be positive. You're not going to get any negatives by plugging in numbers that are 1 or bigger. And just like choice A, this one only has an n in the denominator, so it's going to be bottom heavy. It's going to get smaller as n gets larger. So this one is also continuous, positive, and decreasing for n greater than or equal to 1. So we can also use integral test to determine convergence or divergence for this one. For this next one now, is cosine and e to the n, those are definitely continuous. There's no way to make e to the n equals 0. So we're not going to run into any continuity issues. Where we do run into an issue is that cosine of n is positive and negative for different values. Cosine is negative for some values that are greater than 1. For example, how about pi? Cosine of pi is negative 1. So that violates the negativity, positivity part of this precondition for the integral test. Because cosine's not positive for all n greater than or equal to 1, integral test cannot be used to talk about convergence or divergence for this series. So this is looking like our answer right here because it's the only one so far that can't be used with integral test. But let's take a look at choice D just to really satisfy ourselves here. So this one, and note that we're starting at n equals 2. For this one, there's no discontinuities for n greater than or equal to 2. And we're also going to be positive because we're plugging in numbers that are larger than 1. So that means that ln of whatever you're plugging in is going to be more than 0. And this is also going to be decreasing because n grows faster than ln of n, at least once you get to numbers 2 or higher. So this also meets the conditions of the integral test, and integral test can be used for choice D. So then it is choice C after all, and that's all we have to say on this one. For this problem, we want to know which of these 3 series diverges, and it could be more than one of them. So let's take a look at each one. Harmonic series is known to diverge, so definitely a yes for that one. These next two are p-series. So if you have a p-value that's less than or equal to 1, like this 1/4 here, that's going to show that you're diverging by the p-series test. So that's a yes for that one, for diverging. If you have a p-value like this one pi here, where you're greater than 1, that means that you're converging by the p-series test. So we were looking for diverging series, so that one's a no for this problem. So we just pick the answer choice that has 1 and 2, which is going to be choice C. For this problem, the integral test can be used to conclude which of the following statements about the infinite series n over n squared plus 1 is true. So we have statements about the series converging or diverging, but that's not all of it. They also talk about whether the terms of the series have a limit of 0 or not. So we should probably take a look at the limit of the series as n approaches infinity, just to get that piece of it out of the way. At the very least, that could narrow down our answer choices. So if we take the limit to infinity for that, this is a bottom-heavy function, so this is going to go to 0 for that nth term limit. So that means, let's see, we have a limit of 0, so choice A is still in the running. This thing could converge with a term limit of 0, and it could also diverge. We haven't proven anything yet. It could still diverge. The integral test is going to clear that up for us. But we're choosing then between choices A and B. C and D both talk about the limit not being 0, so we can eliminate those right off the bat. So this problem takes a while, so if you were pressed for time on a test or something, you could at least get it down to A and B and quickly pick one of those. But if you want to know the true answer, we need the integral test. So before we do that, let's just verify we can even use it. For integral test, you need a function that is continuous, positive, and decreasing for, in this case, n greater than or equal to 1. If we look at this, this function doesn't have any discontinuities. There's actually no way to zero out that denominator because n squared can't be negative, let alone negative 1. It's all going to be positive because, again, you can't, for at least if you're plugging in n values that are 1 or greater, there's no way to get any negatives anywhere in here. And also, it's going to be decreasing because, as we saw here with this limit, this is a bottom-heavy function. It gets smaller as the value of n grows because the denominator grows faster. So we have all those conditions, positive, continuous, decreasing for n greater than or equal to 1. So we can use the integral test. That means that if I take the integral of this thing from 1 to infinity, whatever the integral does, that will tell us about what the series is doing. Okay, so let me write an improper integral here. Actually, let me go straight to the limit form of this. So limit as b approaches infinity, integral from 1 to b of what we have here. And we see very quickly here that this is not going to be a one-step integral problem. For this one, I do notice that I have an n squared plus 1, and the derivative of n squared plus 1 has an n, which is also in the problem. So I'm thinking maybe substitution could work on this. I can't really split up this fraction and use partial fractions or anything like that. Integration by parts is kind of overkill if it would even work on this. So let's try substitution with a u value of n squared plus 1. So the derivative there is going to be du equals 2n dn. And we don't need that plus 1 there. There we go. That's better. Because that 1 is a constant, so taking its derivative would just make it be 0. So now we have to divide by 2n to get dn by itself, because eventually we're going to substitute for this dn. So we have du over 2n. And I also have to replace the limits of integration with u values. Right now they're n values. So if n equals 1, then u is going to be 1 squared plus 1, which is 2. And if n equals b, then u is going to be b squared plus 1. So replacing things here, we have the limit as b approaches infinity of integral from 2 to b squared plus 1 of, we're going to have n over u, and instead of dn, we're going to write du over 2n. And we're almost ready to take the antiderivative, but let's clean up a little bit here. So these n's can cancel, leaving me with this expression here. So if you're wondering where that 2 went, look here, I pulled it outside, so we just have a 1/2 out there. No big deal. So now let's go ahead and take that antiderivative with respect to u. 1 over u antiderivative, that's going to be ln absolute value of u, evaluated from 2 to b squared plus 1. Still have that 1/2 out there. Still have the limit as b approaches infinity. So now evaluating this, let me plug in these two limits of integration. We've got 1/2 outside. Inside, we have ln of b squared plus 1, and I don't need the absolute value anymore because this couldn't possibly come out negative. And then I also have ln of 2 that we're subtracting. Now, as b approaches infinity, this ln of b squared plus 1 term is going to grow to infinity. So this whole integral is going to be infinite. It's going to diverge, which means that the series itself is going to also diverge. So between our answer choices, that means B is the answer. Series diverges, and the terms had a limit of 0. For this problem, integral test can be used to conclude which of the following statements about n over e to the n series. So we're talking about it converging or diverging, and the limits of the limit of the terms of the series being 0 or not being 0. So let's start with limit as n approaches infinity of this expression, n over e to the n, just to see what the limit of the terms is. So because exponential grows way faster than polynomial, this is a bottom-heavy function, so this is going to go to 0, which confirms choices A and B. C and D couldn't be it because these say the limit is not 0, so we can already eliminate half the answer choices, which is pretty good for the few seconds it took us to do this. But now to get the actual answer between these two, we absolutely need to use the integral test. Well, let's actually make sure we can use it first. We need a function that's continuous, positive, and decreasing on the interval of n greater than or equal to 1, at least for this problem, or at least some interval with n. So taking a look here, this is going to definitely be positive if I plug in n values that are 1 or larger, because e to the n is always positive, and if you plug positives into n, well, it's going to be positive. It's also going to be continuous. There's no way to make this thing be undefined. E to the n is always going to be a positive number. It can never be 0. And this is also going to be decreasing because, as we saw here, it's a bottom-heavy function. So continuous, positive, decreasing for n greater than or equal to 1. That proves that we can at least use the integral test. So now we're just going to take the integral of this thing from 1 to infinity, and it'll either diverge or converge, and that'll tell us about the series. So for this, I'm going to need to use improper integral reasoning. So I'm just going to skip straight to the limit part of it. So I'm going to have the limit as b approaches infinity of the integral from 1 to b of n times e to the negative n, I'm going to write that as. And you'll see why I do this in just a sec. So thinking about how you can integrate this, this is one of those where we can't use substitution. Partial fractions definitely not even close to being usable on this. And this is not a one-step kind of thing. There's no rearranging or simplifying. That leaves kind of our last-ditch effort is going to be integration by parts. So let's go ahead and write this out. So I'll start by writing out my formula first. So we have the limit as b approaches infinity of, and here's my integration by parts formula. I have uv integrated from, or valued from 1 to b, minus integral from 1 to b of v du. So now I have to find u and v and du. Let me start with my u value. So I have a choice between an algebraic and an exponential. My acronym LATE tells me algebraic makes a better choice for u than exponential. For our u value, we want something that's easy to differentiate. For dv, we want something that's easy to integrate. So I'm going to go with the exponential for dv. So my u value, we'll let that be n. dv then, I'm going to have e to the negative n dn. du is going to just be 1 dn. And then for v, the antiderivative here, the reason I picked the exponential for dv is it doesn't get too much worse when I take the antiderivative. It's just going to be negative e to the negative n. So doing my little 7 pattern here to write things out, I'm going to have limit as b approaches infinity of, and now here's the uv part. This will be negative n e to the negative n, evaluated from 1 to b, minus, now I have a negative negative, so this is going to be a plus integral from 1 to b of, it's just going to be e to the negative n dn in there, because there's just a 1 being multiplied in there as well. And I can go one step further here and take the antiderivative of this expression, so that's going to be negative e to the negative n, which I can lump together with the rest of this evaluation box, since everything's being evaluated from 1 to b. And now it's time to plug in b and plug in 1. So I'm going to write these with the fraction form kind of in there. So I'm going to have negative b over e to the b minus 1 over e to the b. And then I'll essentially do the same thing but with 1 instead of b and subtract all that. So as b approaches infinity, the stuff with this e to the b on the bottom is going to be bottom heavy, and that's going to go to 0. So that just leaves us with all the stuff over here. Well, you've got basically negative 2 over e, but we have a negative out here, so that's positive 2 over e when all is said and done. The really important part of this is that we got a number. We didn't get an infinity or some other kind of does not exist. So because this integral converged, that tells us that the series in general converges. So that means we have to pick answer choice A. The series converges, and the terms of the series have a limit of 0.